Well, here we are. We have come to the end of the road to the last lecture of Physics 1750. And this is a nice capstone to end things on, because we are going to take all of our circuit knowledge and put it together. We're going to examine what happens when you put inductors, resistors, and capacitors all in the same circuit, and the final behavior is mathematically very challenging. No getting around the fact that the differential equation you wind up with is quite a headache. But something that is very helpful is that the equation which describes the behavior of the LRC circuit is actually the exact same one that describes the behavior of a pendulum, which means that in my describing the behavior of the LRC circuit, I'm going to lean heavily on the analogy of a pendulum or pushing a child on a swing or things like that. And we will see that that helps us build our understanding sort of around the fact that what's going on in a circuit can maybe be conceptually challenging to wrap your head around. So let's get started. In this circuit, we're going to put everything together. We're going to start with sort of the ideal case of what happens when there's no resistance. Then we're going to throw the resistances and see what happens for DC-driven and AC-driven circuits. We haven't done a lot of AC analysis in this class, and we're certainly going to keep the math behind it to be very simple, but there's just such an important application here that you can't help but dive in even without the full mathematical picture. But we're going to start here with the idealized case of no resistance. These are for superconductors. We're going to ask what happens in this circuit here, where we start with a capacitor and an inductor just in series with each other, and the capacitor is given some amount of charge, and we're going to then close the switch to see what happens in this circuit. And I'm going to attack this behavior purely conceptually to begin with, and then we'll throw in the math. Well, it's a bit of an odd approach, but we're going to sort of fully rely on these conceptual behaviors of the fact that we know what capacitors generally want to do. In the absence of a battery, the capacitor wants to discharge. And we think of the inductor as this, again, current limiting or current preserving object that always tries to keep the current where it is. So the final result is going to be some competition between these two behaviors. And I'm going to represent that on my graph here by sort of going step by step and saying what the inductor wants to have happen, what the capacitor wants to have happen, and then the actual is going to be some combination of the two here. And let's start with the scenario at hand, which says we're plotting charge over time, and we have begun with the capacitor having some amount of charge here. So this is what the problem has told us where we are beginning. Well, if I asked what does the capacitor want to do, of course, the capacitor is always looking to get here. It always wants to get to Q equals 0 of completely discharged. So the capacitor says, heck yeah, let's get discharged. But the inductor actually is in opposition to this, because the inductor says, I want to keep the current where it was. And initially, this was an open switch, absolutely no current allowed to flow. So it says, right after closing the switch, I again want no current. And no current on a graph of charge means keeping the charge exactly where it is. If that charge were to change, that would mean that you had current. So the actual behavior is going to be something in the middle of these. It's going to say, you can get down to 0 charge, but you sort of had to build up the behavior of getting there slowly. Okay, now that we're here, now what wants to happen? Well, the capacitor says we are discharged and I would like to stay there. No need to do anything else. But the inductor says, oh look, by the time we got here, lots of charge was moving around. And if you were to just halt it in its place, that would mean a massive immediate change to the current. So what the inductor wants to do is preserve this motion of charge. The inductor wants us to overshoot because getting to this discharge state meant building up a lot of current, which you can't just take away instantly. So you wind up overshooting the fully discharged state. And we wind up here. Where finally we got to this spot where the current got back down to 0. And we ask again, what wants to happen? The capacitor says, well, we overshot. I would like to get back down to discharged. But the inductor says, we just got here and we just stopped the current. You can't reverse it immediately. I would like to stay exactly where we are. And you can see the sort of trade-off of what's building up here. We're building up to an oscillation. If I clear off all of my intermediate data, you can see through this competition of what the inductor wants to have happen and what the capacitor wants to have happen, we wind up overshooting discharged every time, and we keep bouncing back and forth. And we have developed sort of on a qualitative level oscillations. And you would get the same thing for a circuit that looked like this. If you threw a battery in, it would try to build up charge on the capacitor, but you would overshoot thanks to the inductor wanting to preserve the current that got you there, and you would sort of bounce up and down across the fully charged state, thanks to the sort of momentum imparted by the inductor. And this is a critical behavior. Anytime you wind up with an inductor and a capacitor in the same circuit, you get oscillations. And oscillations are a big deal from an engineering perspective. Clearly, anything that has music to it requires oscillation. These could be speakers, microphones, whatever it is, absolutely are going to involve inductors and capacitors in the same circuit, because as soon as you put them in the same circuit with each other, you are going to get oscillations. Other very important applications of oscillations, which are tapped into in a circuit perspective with inductors and capacitors, are radio waves. That radio waves are just electromagnetic disturbances these electromagnetic waves being broadcast and sort of sent out across the air. And those electromagnetic waves are themselves oscillating behaviors. So if you would like to emit those electromagnetic waves, if you would like to put out anything that oscillates, lasers, radio waves, it's got to have some kind of inductance and capacitance in it to generate that oscillation in the first place. And we'll also see that the reading of that, sort of the receiving of these waves, is also quite important. So this is a big benchmark for us, having found oscillations within the circuit. And we did this qualitatively to begin with, so it would be nice if we could develop a more rigorous approach. Now we're going to dance around the edge of this a bit, because I'm not looking to get too deeply into the differential equations here, but it is not awful. We would start with the loop rule. We would say any voltage you gain over the capacitor must be equal to that which you have on the inductor. And then plugging in Q over C and L times the derivative of current gets us this relationship from the loop rule. I could recognize that current is the derivative of charge, and taking the derivative of the derivative just gives us second derivative. And now we wind up with a differential equation, again, nasty object, that involves Q and its second derivative. It is now asking us our final answer for how the charge behaves over time is going to have to satisfy this equation where the second derivative to Q is proportional to Q. Whatever function we choose for Q needs to cancel with its second derivative after multiplying by some constants. Well, what kind of function doesn't change much after taking two derivatives? You may think exponential, that's true, but taking an exponential and differentiating it twice is going to give you back the same thing up to constants. But we need these two to cancel with each other. We need a function which switches sign after two derivatives. And that's where sine and cosine come into play. Because after two derivatives, they bounce back and forth from sine to cosine and back to sine, with a minus sign sort of coming along for the ride. So these oscillating functions are a perfect choice, and they come very neatly out of the math here in the differential equations. And it identifies a frequency for us. The frequency at which these things oscillate is called the resonant frequency, and it's 1 over the square root of the inductance times the capacitance, a value which will be very important in choosing the frequency at which you want your circuit to oscillate. Because, of course, that's going to be very important if you're looking to, generate music, where the frequency of that music needs to be very carefully controlled with these kinds of values. Okay, so we have seen the qualitative and quantitative behavior of this no resistance limit of inductors and capacitors. We have seen that anytime you put them together, you immediately get oscillations. The next obvious question is, what happens when you add the resistance back in? Well, sticking with the purely conceptual picture, we know the role the resistance plays in the circuit is that it's this object which burns energy. It is this natural friction to the circuit. So where we used to have oscillations that just bounce around forever, now, of course, resistors are going to come in and take away energy. They're going to sort of squeeze the behavior and take out the energy of the oscillation rather than leaving it conserved the whole time. And the value you put on that resistance is going to change the rate at which that happens. That if you have very small resistors, it's like having a pendulum with very little friction to it. It will continue to oscillate, and it will wind up sort of eventually losing its energy over time. If you have a pendulum, now as you increase the resistance, it seems like it slows down and it stops oscillating, but at some point you can get so big with your resistance that it actually takes longer, that you can it's like imagine releasing a pendulum under oil, that it takes forever to sort of sink its way back down. Now, the math behind this transition from oscillating to not oscillating and then taking a long time to get down is all quite involved and kind of beyond the scope of what we need to do for this course. But I hope at least from a conceptual outlook, this makes some sense. That with different values of the resistance, we wind up with different behaviors. For absolutely no resistance, the circuit will just continue to oscillate forever. For some small amount of resistance, it will continue to oscillate, but it'll die out over time. And then at some point you transition over into this state where it no longer oscillates, and it sort of just dips down without passing over. And then as you go further, it's the same behavior, but now taking longer and longer and longer because you're slowing down the rate at which it can even get back to equilibrium in the first place. There's a transition from one to the other, which is 2 times the square root of L over C. Not a value that I intend for us to use, but it's something that you can have in case you need it in other applications. But we're staying pretty much qualitative here. Now, given that we've sort of developed a qualitative look at what the circuit is going to look like over time, it is undeniably challenging to figure out the entire mathematical function from 0 to infinity. But as we have done with the RC circuit on its own and the LR circuit on its own, it is nonetheless possible to analyze the limits of t equals 0 and t equals infinity without diving into the nasty math. So try doing it here. Try seeing what would be the behavior of this circuit after a very long time at t equals infinity. Pause and give it a thought. Okay. I hope you found that after a very long time, everything's going to go down to 0. We started with a fully charged capacitor here, and it will release its charge and sort of send it oscillating through the circuit, but it's going to die out over time. And eventually, all of that motion is going to stop. We wind up with no current in the circuit. The capacitor has nicely equilibrated itself and gotten back down to 0 charge. And since we're at 0 current and we're staying there, we're at steady 0 current, the inductor has, of course, also gotten down to 0. What about for this circuit? Try it here where it's a discharged capacitor, and now we're going to enter this oscillation of charging up the capacitor and trying to get to fully charged. See what you think here. Okay, this time the capacitor winds up with a non-zero voltage, but everything else has 0 voltage on it other than, of course, the battery. Because the conceptual behavior here is we try to charge the capacitor, but we overshoot, and we keep sort of bouncing on either side of overcharged, undercharged, overcharged, undercharged. And then the resistor sort of squeezes us in over time to equilibrium. But once we've reached equilibrium, there's no more current, and we're at steady current, and we're fully charged. So 0, 0, full voltage. All right. So you can see we're still able to do some of our basic circuit analysis for t equals 0 and t equals infinity, where everything in the middle is probably going to be very complicated. Okay, so that's an important perspective to have on the RLC circuit. This DC-driven behavior of what happens when you put a battery into the 3. But the real glory, the sort of real magic of the RLC circuit, where it really starts to shine, is where you're not hooking it up to a battery, but where you're hooking it up to an AC voltage source. Now, this is important for multiple reasons. One, modern circuitry sort of coming out of wall outlets is AC. And for two, we see that we get some really important behaviors out of this. So when you, instead of driving the circuit with a constant push, that would be like, if I go back a few slides, driving this pendulum with a fan, sort of turning a fan on, creating this big wind and sort of pushing the pendulum off to some new equilibrium with a constant force. What happens if you instead move to a setting where your pushing force, the thing you're using to drive the circuit, is also oscillating? This is like you pushing a child on a swing with not just a constant push, but rather something that oscillates over time. You would never just keep shoving a child on a swing. Well, we know that the circuit wants to oscillate at some behavior. So if you're going to choose what frequency to push the circuit at, you might expect that different frequencies give you different responses in the circuit. If you have a child on a swing, you know that the swing has this natural frequency at which it wants to oscillate. That's the frequency it'll oscillate just when left to swing on its own. And if you push at that nice frequency, you get really nice big swings. But if you push too fast or too slow, you don't wind up getting the full effect. Imagine pushing a child on a swing where you just push, wait, 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 push. You're not ever going to get that much. And if you sit there going push, 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 you sit there shaking the child really fast, also not going to get very big oscillations. But if you push at the resonant frequency, if you drive it at this frequency it wants to oscillate at, you end up getting really big results. And what we're seeing here is this conceptual behavior of the size of oscillation you get in the circuit here, what I'm describing with the amplitude. The amplitude of the oscillation in the circuit is biggest when you drive it at the resonant frequency. And if you drive it too fast, it will start to shrink. If you drive it too slow, it will start to shrink. It will always oscillate at the frequency you tell it to. Just like if you grab onto the chains of the swing and force it to oscillate with your hands, it will oscillate at the frequency you tell it to. But you get the biggest and nicest result at the resonant frequency. And there are lots of engineering applications to this idea of any oscillator has a resonant frequency, a frequency at which it wants to oscillate at. And if you push it at that frequency, you're going to get really big oscillations. Even the little tiny oscillations within the sort of vibrations of the material that make up a bridge are themselves oscillators. And they have a frequency that they want to oscillate at. And if the wind comes along and sort of pushes and sort of gets these vibrations at just the right frequency, you get some devastatingly large oscillation. And on a smaller scale within a circuit, you can do the same thing. If you push on the circuit at the right frequency, you'll get very large oscillations in the circuit. So take one final chance, sort of using our understanding of the fact that a circuit wants to oscillate at its resonant frequency. And if you're off by that frequency, it'll be smaller. See what you think, and sort of putting all these analogies together of pushing children on a swing and thinking of all these conceptual behaviors. One last checkpoint to pause and think. How many of these options would wind up giving you bigger oscillations in the circuit? Give it a moment. All right. Turns out that only 4 do. And how do you know this? Well, we know that if we are not at the resonant frequency, it means that we can do better. It means that we are, say, if I want to shift over and draw this, where on the x-axis here is the frequency at which I drive it, and on the y-axis is the amplitude. It means we're off the resonant frequency. We're either here or maybe we are too fast. And if we want to make the oscillations bigger, well, we have a couple of choices here. We could move and get closer to the resonant frequency. We're not sure whether or not that means get bigger or get smaller, but certainly one of those will help. We're not sure which, but of these two options near the bottom, one of those is guaranteed to get us closer to the resonant frequency, and therefore one of those is bound to help. Thankfully, this problem's not asking you for which ones, just to count. So it's definitely one of the two of these. Or, sort of a clever idea is that you could keep your driving frequency the same and shift the resonant frequency. You could move the resonant frequency to be where you are at and sort of naturally matching up. And there are, of course, multiple ways to change the resonant frequency. Increasing either L or C is going to decrease the resonant frequency, and decreasing it will increase the resonant frequency. Again, we're not sure if we're above or below, but two of these are going to help. We're not sure which two, but certainly two. So we're up to 2 out of these 4 and 1 out of these 2, and then the fourth is this last one. That, of course, just pushing harder, so this is you legitimately with your arms pushing harder on the swing, is going to give you a bigger amplitude. It's kind of this magical property that if you want bigger oscillations, of course the natural intuitive answer is push harder, but it's so incredible and so important that the rate at which you push has just as big of an effect. And so there it is. We sort of put all of these together, and these will be important for you in sort of working on the last simulation. One other very important factor to this behavior of the size of the oscillation depending on the frequency at which you drive it is this idea of a quality factor. Sort of what's the shape of that fall off? Is it something where it's robust, where you can get pretty far away from the resonant frequency without falling off too much? This is like, imagine a swing where you're not perfectly on the resonant frequency. You're not able to quite figure out the perfect rate at which to push the child. You might be interested in understanding what the quality factor is of understanding how tolerant is the swing. If you're slightly off, how much is that going to matter? If you have a very large quality factor, it's going to matter a lot. As soon as you move just a little bit away, you're falling very steeply off of your maximum. Versus something with a small quality factor says, you didn't fall too much, which is an important quantity to understand. And it's calculated with formulas which are definitely not going to get derived, but are nonetheless things that are going to be helpful with this relationship of 1 over r times the square root of L over C. It tells us sort of this measure of how thick and how tolerant your circuit is to changes in frequency away from resonance. Now, the first thing that should come to mind is, who really cares about that? I mean, yes, I've tried to motivate it as this important relationship between sort of this error rate of if you miss resonance, how much does that matter? But it actually has a more practical application in the receiving of radio waves. Because when we have a circuit that is designed to pick up radio waves, we have to choose the means by which we do so very carefully. And we pick up those radio waves as electromagnetic disturbances, as electromagnetic waves through air, and we use those electromagnetic waves to power the circuit. They are sort of playing the role as the driving frequency of the circuit. So let me sort of set up a scenario for you. Because if I want to be tuned to one frequency, I need to be very careful here. So let's say, as a function of frequency, there's the radio station you like. And they want to put out their radio, their band, their information at some frequency. This is the frequency that you are tuning into on your radio. Now, they're not perfect at doing that. They, unfortunately, aren't able to broadcast everything at this perfect frequency. It gets sort of messed with a little bit because we're never able to give out perfect information and never able to put out at exactly a perfect frequency. So they wind up putting out at a small range of frequencies. So if you're going to design your circuit, you would like it to have a quality factor big enough to pick up on all of the frequencies that that radio station is putting out. If you had a quality factor that was too small, you might miss out on all of that extra information that was being put out by those EM waves. But then you could just say, well, okay, why don't I just pick the biggest quality factor I can? Well, if you're too big, now you accidentally start picking up on other radio stations. So it becomes this sort of delicate balance to pick up, to be big enough to pick up everything that the radio station is putting out, but not too big where you start accidentally picking up others. And choosing that is very careful, that you need to choose the inductance and capacitance to be at the right resonant frequency to match the radio station's resonant frequency, the frequency that the radio station is trying to put out, but also choosing your inductance and your capacitance and your resistance very carefully to have the right quality factor, neither too big nor too small. And it turns out that means, in designing your circuit, you want to then have flexible control over the resistance, the inductance, and the capacitance. And what's being shown here is what that looks like from an engineering perspective. What you're seeing here in this animation is a variable capacitor, where by sort of moving the capacitor plates around like this, you're sort of changing how close they are to each other, in effect kind of changing the D in epsilon A over D, which is allowing you to sort of tweak the capacitance, to tweak the resonant frequency and the quality factor as you go. Same here with the variable inductor. We know that the inductance of a solenoid depends on how many coils it has. So by turning this knob, you sort of change the contact point, changing how many coils you're actually using. And that sort of, in effect, allows you to vary the inductance as well. So you would twist these two knobs until you got to the right resonant frequency with the right quality factor. And that's how old primitive radios worked. Those were the knobs you were actually twisting, were these factors here. Now, of course, that's all digital now, but it's kind of cool to see where that comes from. And you'll be playing with much the same concepts in your simulation of tuning and finding the right inductors and capacitors to have the right quality factor with the right resonant frequency. Well, that'll do it. That'll do it for Physics 1750. We have seen electricity, we have seen magnetism, and we have seen how they both come together in circuitry. It's been a wild ride, but it's been a pleasure working with you all. And please let me know if you have any questions, either now or moving forward as you sort of start applying these things in your various engineering classes. I will always be happy to help you moving forward. Please don't lose touch with me. Please let me know if I can ever help with anything down the road. All right, take care.